Albert Einstein, a name synonymous with genius, forever changed our understanding of the universe. Born in Germany in 1879, Einstein's inquisitive mind challenged long-held scientific beliefs. His theories of relativity, developed in the early 20th century, revolutionized physics and laid the foundation for modern cosmology, astrophysics, and our pursuit of space exploration. Before Einstein, physicists viewed space and time as separate, unchanging entities. Newton's laws of motion and gravity reigned supreme, accurately describing the movements of planets and stars. However, as our understanding of the universe deepened, cracks began to appear in this seemingly complete picture. Einstein's genius lay in his ability to see beyond these cracks, to imagine a reality far stranger and more wondrous than anyone had dared to imagine. Einstein's theories of relativity, divided into special relativity and general relativity, provided a new framework for understanding the cosmos. These theories were not mere refinements of Newtonian physics, they were a radical departure, overturning centuries of scientific thought. In the vast cosmic dance of planets, stars, and galaxies, Einstein's theories provided the music, a symphony of space and time intertwined. His work transcended the realm of pure science. Einstein's theories seeped into popular culture, becoming synonymous with genius and complex scientific concepts. He showed us that the universe is not a static, unchanging stage, but a dynamic and ever-evolving entity. And within this cosmic dance, his theories revealed the profound interconnectedness of space, time, and gravity. Einstein's revolutionary ideas about the universe are encapsulated in his two theories of relativity: special relativity and general relativity. Often perceived as separate entities, they are in reality two sides of the same coin, each illuminating different facets of the cosmos. Special relativity, published in 1905, focused primarily on the relationship between space and time. This theory, born from Einstein's thought experiments about light, shattered the Newtonian notion of absolute space and time. It presented a universe where the speed of light remained constant, regardless of the observer's motion, a concept that had profound implications for our understanding of the cosmos. General relativity, published in 1915, expanded on special relativity by incorporating gravity into the equation. Einstein proposed that gravity is not a force acting across space but rather a curvature of space-time itself, caused by the presence of mass and energy. Imagine a bowling ball placed on a trampoline, causing the fabric to sag. This is a simple analogy for how massive objects warp the fabric of space-time, influencing the motion of objects around them. While special relativity excelled in describing the universe on the grandest scales, dealing with the motion of galaxies and the vast expanse of the cosmos, general relativity provided insights into the behavior of extremely dense objects like black holes and neutron stars. It offered a framework for understanding the evolution of the universe itself, giving birth to the field of cosmology. Together, these two theories form the bedrock of modern physics. They provide the lens through which we observe and understand the cosmos, from the subatomic realm to the largest structures in the universe. And it is within the framework of these theories that we continue to unravel the mysteries of the cosmos and explore the vast expanse of space. At the heart of Einstein's special relativity lies a deceptively simple yet profound concept. The speed of light in a vacuum is constant for all observers, regardless of their relative motion. This postulate, seemingly at odds with everyday experience, has profound implications for our understanding of space and time. Imagine chasing after a beam of light. Intuitively, you might expect to perceive the light traveling slower, as if you were catching up to it. However, special relativity tells us otherwise. The speed of light remains constant, clocking in at approximately 299,792,458 meters per second, regardless of whether you're standing still, running towards it, or flying alongside it at unimaginable speeds. This constancy of the speed of light has mind-bending consequences for our perception of time and space. It gives rise to phenomena like time dilation and length contraction, concepts that seem ripped from the pages of science fiction, yet are very real consequences of Einstein's theory. Time dilation, perhaps the most intriguing consequence of special relativity, suggests that time is not absolute but relative to the observer's frame of reference. Imagine two identical clocks, one stationary on Earth and the other traveling at a significant fraction of the speed of light. Special relativity predicts that the clock in motion will tick slower relative to the stationary clock. The faster the clock travels, the slower time passes for it, an effect that becomes increasingly pronounced as we approach the speed of light. Length contraction, another bizarre consequence of special relativity, states that the length of an object moving at a high speed appears to contract in the direction of motion, as observed from a stationary frame of reference. This contraction is not a physical squeezing of the object, but rather a consequence of the relative nature of space-time. Imagine a spaceship traveling at near light speed. To a stationary observer, the spaceship would appear shorter in the direction of its motion. These concepts, though seemingly counterintuitive, have been experimentally verified countless times, solidifying special relativity's place as a cornerstone of modern physics. They illustrate the interconnectedness of space and time, revealing a universe far stranger and more wondrous than we could have ever imagined. Section 4. Time travelers beware, the curious case of the twin paradox. Perhaps the most intriguing illustration of time dilation, a mind-bending consequence of special relativity, is the famous twin paradox. This thought experiment, often a source of fascination and debate, vividly portrays the relative nature of time and its implications for space travel. Imagine identical twins, let's call them Alice and Bob. Alice remains on Earth while Bob embarks on a high-speed journey through space in a rocket capable of approaching the speed of light. After a predetermined time, Bob returns to Earth, having aged significantly less than his Earth-bound twin, Alice. How can this be possible? The answer lies in the heart of special relativity. Because time is not absolute but relative to an observer's frame of reference, time passes slower for Bob during his high-speed journey compared to Alice, who remains in a relatively stationary frame of reference on Earth. From Bob's perspective, time inside the spaceship flows normally. However, from Alice's perspective on Earth, time appears to slow down for Bob. The faster Bob travels, the more pronounced this time dilation becomes. Upon their reunion, Bob will be younger than Alice, a testament to the reality of time dilation. The twin paradox, though seemingly paradoxical, highlights the strange and counterintuitive nature of time within the framework of special relativity. It underscores that time is not a universal constant, but rather a fluid entity, intricately woven with space to form the very fabric of the cosmos. While the technology for such high-speed space travel remains beyond our grasp, the twin paradox serves as a tantalizing glimpse into the potential implications of special relativity for future interstellar voyages. It suggests a future where astronauts venturing into the cosmos could return to Earth younger than their Earth-bound counterparts, having experienced time at a different rate. Section 5. The Fabric of Reality, Introducing General Relativity. In 1915, a decade after revolutionizing our understanding of space and time with special relativity, Albert Einstein presented the world with another groundbreaking theory, general relativity. This theory, often hailed as Einstein's masterpiece, provided a new and profound understanding of gravity, not as a force acting across space, but as a curvature of space-time itself. Imagine a bowling ball placed on a trampoline, causing the fabric to sag. This simple analogy helps visualize how massive objects like stars and planets warp the fabric of space-time, creating what we perceive as gravity. Objects moving through this warped space-time follow curved paths, a phenomenon we experience as the gravitational pull of massive objects. General relativity departed radically from Newton's law of universal gravitation, which had reigned supreme for centuries. Newton's theory, though effective in describing the motion of planets in our solar system, failed to account for certain subtle gravitational effects, such as the precession of Mercury's orbit. Einstein's theory, however, accurately predicted these anomalies, providing a more complete and accurate description of gravity. It proposed that the very fabric of the universe, space-time, is not a static backdrop, but a dynamic entity, warped and curved by the presence of mass and energy. This warping of space-time has profound implications for our understanding of the cosmos. It affects the motion of objects, the passage of time, and even the path of light. General relativity predicts that light itself, though massless, is influenced by the curvature of space-time, bending around massive objects like stars and galaxies. This prediction, confirmed during a solar eclipse in 1919, catapulted Einstein to international fame and solidified general relativity's place as a cornerstone of modern physics. General relativity's impact extends far beyond explaining gravitational anomalies. It provides the foundation for our understanding of black holes, neutron stars, and the evolution of the universe itself. It continues to guide our exploration of the cosmos, leading us ever closer to unraveling the mysteries of the universe.